Okay, so the first part, part A, should have reviewed a little bit just making a parent function for an exponential graph, okay? So what did you guys get for the values for part A? So our first y value, 1/8. Okay, so as long as we're calculating these negative exponents correctly, then what? 1/4, 1/2, good. 1, 2, 4, 8. Okay. And then where is our asymptote for this function? Y equals 0. So all of our exponential parent functions, remember, they got closer and closer to being 0, but they never actually reached 0 or crossed it. So all those parent functions have this y equals 0 asymptote. Okay? So the graph of your exponential function should be as expected if you've looked back at that Cartesian catalog and are familiar with it. You have this asymptote at y equals 0. Okay? And we have -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. Okay? And you have this exponential curve. So that's something we should already know how to do, that we can make this graph at the beginning for any of the exponential functions we want to graph through transformations. Okay? So then the next part says the log and exponential functions are inverses. Okay? And then I asked you guys to create a table just based on knowing that relationship. So tell me a characteristic that we know about inverses that can allow us, without any other information, to create this table. Brandon? Good. Okay, so we saw with inverses, whether we saw it through the geometry of the reflection or through the numbers or through how we found an inverse, was that inputs and outputs kind of changed location. So right here, you used to have the point -3, 1/8. In the inverse of this function, you would have 1/8, -3. Okay? You have -2, 1/4, and the inverse should have 1/4, -2. Okay? So I'm building this function based on what I would do numerically with the numbers here to create the inverse. So this is a property that we're familiar with from the last unit that we ended with second semester. Okay? This is a log parent function. Okay? So you might be like, I don't even want to plug in these numbers, but think about how these numbers would be chosen for the parent function. Remember, you're trying to think of the things kind of surrounding 0 that you'd want to plug in for the log function. We can't plug in 0. We can't calculate the log of 0 or any negatives. So we plug in some things close to 0. So we choose these fractional amounts, kind of show us what's happening on one side. We plug in 1, that gives us 0, and the numbers bigger than 1. But notice the numbers you would choose, because the base is 2, are all different powers of 2. Okay? If the base is 3, I would want to see numbers up here like 1/9 and 1/3 and 1 and 3 and 9, 27. Things that have to do with a base of 3. Does that make sense to everybody? Okay. Where do you think the asymptote would be for this function based on how the inverse relationship works? Chris? Good. So instead of y equals 0, I know I don't have room here. I'm just going to write it here. You guys have a space for it in your note guide right below. Our asymptote is at x equals 0. Okay? So I'm going to go ahead and plot these points so that you guys can see it on the same graph as the other. So here's my x equals 0 asymptote. And then I can go ahead and plot those points. 1/8, -3. That's real close to the asymptote. I don't know. 1/4, -2. 1/2, -1. 1, 0. 2, 1. 4, 2. 8, 3. This is our logarithmic curve. Okay? So the graph of a logarithm looks similar to an exponential graph. Okay? But notice an exponential graph tends to take off and grow rather quickly, where a logarithm grows much slower. Okay? Like it will continue to grow forever, but it takes a long time. Okay? Yes, Zen. Yeah, so remember when inverses, to create inverses, right, things that used to be x values became y values, and things that used to be y values became x values. So if the equation of this asymptote here used to revolve around y equaling 0, and when we invert it, x and y are kind of changing positions, then the asymptote here becomes x equals 0. Okay? So our parent logarithms, again, like the exponential logarithms, if they have a different base, you have a different parent. Okay, so that's something new this semester that we've come across, right? There's not one parent function. There could be lots of parent functions for exponential and log functions depending on the base. Okay? For our exponential functions, all the parent functions had y equals 0 as the asymptote, and they all had the point 0, 1, no matter what the base was. What characteristics will be true for all log parent functions? We can say all the log parent functions, no matter what the base is, will have what points or what characteristics, Quinn? Good. They'll all have 1, 0, okay? And they'll all have their asymptote at x equals 0, because unless you put something else in, the limitation on the logarithm is that we cannot plug in 0 or negative values, and that's what you're seeing here with this asymptote, okay? Is everybody okay with like the overview of the structure and where this graph would come from, how we'd know to plug in these crazy numbers for our parent function instead of plugging in our basic values that we got from before? Okay. So now we're going to take this and we're just going to put it into a Cartesian catalog. So here's a picture of what we just graphed, okay? And here's the table I would use for the parent function. Okay, so instead of plugging in -2, -1, 0, 1, 2, you actually see those as the outputs. But again, that should kind of make sense because it's the inverse of the exponential function. The things I would plug in when the base is 2 are some powers of 2 on one side of 1 and some powers of 2 on the other side, because I know all the graphs will have that point 1, 0. So I choose 1/4 and 1/2, then 1, and then 2, and then 4. Ariane? Yes. Mm-hmm. So there's several ways to build this. So one way is to grow comfortable enough with the log function that it doesn't look odd to you when it's log base 2, that 1/4, 1/2, 1, 2, and 4 would be the values you'd choose to create the parent function for this, okay? Another way to do it is to think about what Ariane just said. So instead of saying y equals log base 2 of x, that's like saying 2 to the power of y equals x, and then because y is the exponent, you could choose to put these in for y and get your x values here, okay? Another way to do this is instead of doing 2 tables like we normally do, we normally have one parent table, right? And then one table that gives us our final points after the transformations are done. You could do kind of 3 tables, like a pre-step to starting. And so what you could do is when you base 2, if log is not that familiar with you yet and you don't really like forming this table or you get stumped, you could go build the table for the exponential function with the base of 2, right? And then you could do what we just did. You could take the inverse. But you have to remember that that first table is not something you would normally do, and it is like a pre-step, okay? And that until you flipped it and made this table, you're not really starting the log graphing process yet, and then you'd have one more table with your transformations. So you just have to really keep track of what you're doing, okay? So either, like Ariane said, rewriting the function and helping you plug in for x and y might be one way. Some of you might be comfortable enough with logarithms to identify with these values right here as inputs, and this is comfortable for making the parent equation. And some of you might choose to do 3 tables instead of 2 tables. One that has the exponential function and gets turned into the log and then gets forgotten about, and then your transformation table, okay? Is everybody okay with an idea? You have like a strategy you think you could use to make sure you can come up with a log parent function if you're graphing logarithms. Okay. So then we're going to look at the properties of that one specifically. So again, just like we mentioned before with the exponential problems, that's probably too small for you guys, huh? So just like we mentioned before with the exponential problems, I don't want to write h and k like a point. It is important for me to identify those values because they do cause important shifts in our function, and they'll affect like the asymptotes and some things like that. But they aren't actually points on our graph because we don't have 0, 0 when we graph a log function, just like we didn't have it when we graph an exponential function. Okay. So our x-intercept, 1, 0, that would be true for every log parent function, right? That would be a point that's there. There was no y-intercept in this one because of our vertical asymptote. Our domain here is only x is greater than 0, so written as an inequality or an interval. And then our range is all real numbers. This entire graph was increasing, and the entire graph only exists on its domain, so from 0 to infinity with no decreasing interval. Okay. We are 1 to 1, and we're not going to be worried about rate of change or axis of symmetry. No minimum value, no maximum value, no horizontal asymptote in this case, but a vertical asymptote at x equals 0. Okay. So take a minute to process that information, get down some of the notes, and then see if anyone in your group has any questions about the log parent function. That is our emphasis right now. Let me pause it. I walked, but I didn't pause. You guys don't want all your questions on the video, right? Build the parent function when you have them. If they're a different base, then you'd use a different base. So is everybody okay with the way that this function is written? That my transformations would be a shift 3 to the left, a vertical stretch, and a shift up 1. So first of all, are there any issues with the transformations I just said and how they're written right there at the top of that table? So everybody notices the base of 2 is not a transformation. The 2 that's up there is from the 2 written at the very beginning in front of the logarithm. Because remember, the base is part of the parent function, not part of the transformation. Okay? And so then we took each of the values there and did this to them. And yes, you guys will either have to do some fraction arithmetic or understand fractional values from numbers pretty well. And then we took the y values and did this to them. And so we have our new graph. Notice our asymptote at x equals -3. What is a way that you could quickly identify your asymptote for the logarithm functions? Hunter? Good. Okay. So with exponential functions, we had a horizontal asymptote, and the only thing that would change that asymptote is shifting it up or down. With logarithms, you have a vertical asymptote. What's the only change that's going to adjust that asymptote? Shifting it left or right. Okay. So the fact that it's at -3 is solely based on that h value from your guys' equation. Okay. Any questions about our points or our graph on here? Okay. So notice that there is an x-intercept. You can see it on the graph, right? The graph crosses the x-axis, correct? Okay. And I did not put an x-intercept yet at the key because until the end of this week, you guys have not yet learned how do I solve it when I put 0 in for y there. X is trapped inside of a function called the logarithm. How do I get it out of the logarithm? And we haven't technically gone through that process yet. So there is an x-intercept here. We are just not writing it yet, and we're going to have to come back to this and solve for it once we figure out how we solve equations that have logarithms in them with x inside. Okay? For the y-intercept, I plug 0 in for x. Okay? When I plug 0 in for x, 0 plus 3 gives me 3. So I have 2 times log base 2 of 3 plus 1. Without a calculator and a special formula, which we'll look at tomorrow, but without a calculator, that's as far as you can get because log base 2 of 3 means 2 to what power gives you 3. Is 3 a power of 2? No. That doesn't mean there's not an answer. It means the answer is something weird like fractional or something like that. And we just aren't expected to know that off the top of our head. If this had been a 4 in here, I would expect you guys to calculate further because I would expect that you would be able to do without a calculator log base 2 of 4. What's log base 2 of 4? 2. And then you'd say, oh, that's really just 2, so that means 2 times 2 plus 1. log base 2 of 3, I do not expect you to do without a calculator. But anything that can be written as a power of 2, I would expect you to be able to calculate log base 2 of it. If it can't be written as a power of 2, that's as far as we can go. Okay? Is everybody okay with why I didn't write an x-intercept in here? We're just lacking a skill right now. We'll come back and do it. And is everybody okay with the y-intercept? No? Okay. So domain and range. So our entire graph exists to the right of that asymptote that's at -3. So our domain is x is greater than -3 or from -3 to infinity. Okay. Our range is all real numbers. The entire graph is increasing. So our domain is also our increasing interval with no decreasing interval. Okay. And yes, it's 1 to 1. So we're not expected to know anything about rate of change or axis of symmetry here. And then minimum and maximum value are none. No horizontal asymptote for the log function, but a vertical asymptote at x equals -3. Okay, Sid? Sorry. Repeat it. Did you guys hear a weird noise? No? Okay. Sorry. Go ahead. Yeah, that's exactly right. Okay. All right. Is everybody okay with the characteristics of that graph? All right. So flip it over. Let's look at the Algebra 2 trig graph. Okay. When you look at the equation on the back, what's the first thing you notice that you're going to have to do? Emma? Good. Okay. So remember that it's not really written in the form that we've studied. Okay. So the first thing that needs to happen here is that I have to look at this 2x minus 4 differently than 2x minus 4 if I want to understand what values are really here. I have to look at the 2 separate from the x minus h package, so I want to look at it written this way. Okay. And is everybody okay that once I write that 2x minus 4 as 2 times x minus 2, it means I have a b value of 2, and like we've seen on the graph, that actually is used like multiplying the horizontal distances by 1/2, so a horizontal compression. And then x minus h means that the 2 as an h value is a positive 2 and shifts to the 2 to the right. Okay. And then I have this reflection and this vertical stretch with a shift down 1. Okay. Any questions about our table? Sorry, my graph is ugly, like my no. Okay, are we all right? So see that started to graph a horizontal asymptote, was like, no, this is not exponential, right? I was like looking at the k value. So looking at the h value of 2, we have this vertical asymptote at 2, okay? And then we plotted these points. Now there was a reflection, but notice the graph is still on this side of the asymptote. That's because you didn't reflect x values. You didn't flip over the y. It flipped over, okay? The y values changed flipping over the x-axis. So the curve still stayed on this side. It just didn't go in the direction that we originally thought the parent would. Ariana? So, because this isn't an exponential function. So, the asymptotes are here in these two functions to describe to us where we can't reach something. So, with logarithms, we can't plug certain things in. So, we've learned we can't calculate the logarithm of 0 or a negative based on what we did on Friday. There's no exponent that gives us those things. So, vertical asymptote is here for logarithm functions because it's like, oh, you can't plug in anything smaller than this. Otherwise, you'll have a 0 or a negative in here, and then this whole thing will be impossible to calculate. With exponential ones, it's this way because you can plug in any exponent you want, but there is no exponent that will make the answer equal to 0 or a negative. And so that was kind of setting a y boundary, like you'll never get anything below here unless you shift it or reflect it or something like that. Is that okay? Any questions about our graph or our points? And again, you guys will have to do some fraction arithmetic or just understand, like, oh, if I take an eighth away from this, I'm left with this, or if I add an eighth to this, I'm left with this. But there's no shame in going off to the side and making common denominators to do your addition or subtraction there and what you have to do. You just want to know where those points are. Okay? So again, I left the x-intercept blank, not because there isn't one, because there clearly is. I can see it crossing the x-axis. I left it blank because we don't have the skills right now to calculate an exact value when I replace y with 0. Okay, so we're going to come back and fill that in. The y-intercept is none. Okay, there's two ways for you to see this. Way number one is graphically. Do you guys see why there isn't a y-intercept? Okay, when we shifted the graph to the right, we made it so that we would never, ever go by the y-axis. Okay? Secondly is algebraically. If you guys went to solve this and you plugged 0 in for x, you guys would get y equals -3 log base 2, 2 times 0 minus 4, minus 1. Look what's happening as you continue this calculation. When you calculate what's inside the logarithm with 0 plugged in for x, 2 times 0 is 0, minus 4 is -4. What is log base 2 of -4? Undefined. It doesn't exist, right? We established when we tried to go through some logarithm calculations on Friday that when there's 0 or a negative in here, there's no exponent you can put on this to make this, okay? So this is how you would know numerically that there's not a y-intercept, because you're trying to do a calculation that doesn't exist. If the calculation doesn't exist, then there's no answer to this calculation. When there's no answer to a calculation, that's how you know you don't have one of whatever it is that you're looking for, okay? Here, our domain is all to the right of 2, so x is greater than 2. Our range is all reals. Annabelle? No. You would just graph it like this. You can visually see here if this is our asymptote. This asymptote helps people see that you're marking that it doesn't go past this point, and they should know that it then cannot hit the y-axis. Is that okay? Yeah. So no increasing interval, the entire thing is decreasing, so the entire domain. It is 1 to 1, and then no min, no max, and we have our vertical asymptote at x equals 2. Okay. Are we okay with graphing logs? Not that different than what we've seen before, because we keep seeing the same transformations over and over again. The different thing, having that vertical asymptote there that kind of blocks off one thing. And the parent function for logarithms is not as simple as a lot of our other parent functions. So again, establish some sort of strategy that you're going to use. Are you going to build an exponential one and then flip it around? So you're going to make like 3 charts. Are you comfortable with the log parent function because you understood them and they sit well with you? Or are you going to rewrite it as like x equals 2 to the y and use those values to build the parent function? So just make sure you have an idea of what you're going to do, because even if you understand this whole process, if you don't have a way to establish a parent function, you can see that you're going to struggle getting the graph on the information, right? So that's going to be a key step for you guys to be able to do. Okay. Any questions about